Group 1 here is a presentation about the field emissions testing. This is what Michael was just talking about. This is an uncontrolled field emissions test in which we're collecting sample from the plume or from a chimney. And we're going to be, this is an example of testing that is done in the home, in which the cook does not change the way that she processes food, cooks, or the fuel. It's simply measuring the stove and kitchen performance as it is done without any changes. In this method, we don't sample the entire plume like is done in the lab. This is done using a partial sample of the smoke. And there are two ways that we're doing this. This is an example of the way that the smoke is collected from a chimney without a stove. So you can imagine a small stove here, and the smoke comes into these probes. If you see closely, maybe later, you can see that there are small holes, and this is where the air is drawn in through, and then imagine the sampling equipment at the other end, which may include particle sampling and CO sampling, and any other gas or measurement that you're interested in. So the method uses what Jim Jetter was talking about previously, the carbon balance method. And this is used to calculate your emission factors in grams of pollutant per kilogram of fuel. Okay? That's the brief introduction. If you have any questions now, we can ask them, and then we can go in and see the equipment. Yeah.
There is some kind of relationship to calculation of the number of points to sample, the diameter of the duct of sample.
Yeah, there are some calculations to do with that. Generally, we try to make sure that it covers the plume so that airflow doesn't draw the smoke away from the probes, and they are such that you have small holes at the beginning and big holes at the end, so that your airflow is more or less even throughout. The velocity is more or less even throughout each of the holes.
Mm-hmm. Can you hold that up one more time? Just see that.
I don't know. Can you see that?
Yeah.
Yeah. And the sampling probe is such that you can use different sizes depending on the environment that's appropriate, so you don't disturb the cook and you have as much coverage of the plume as possible. Inside, we can see the sampling from the stack. We can probably file in now.
What is the name of this?
I'm calling it a probe.
Probe.
Sampling probe.
Sampling probe.
This is just for the non-chimney stove.
This is just for non-chimney stoves.
And there's 16 ports? 16?
There are, it depends actually on the length
Okay.
of the
So
bars.
This is just
So this one
above-
will have three. Yeah.
So this keeps just above the stove.
It's just above the stove. Yep.
Yeah. Sometimes there is a backfire from the stove, and then directly it goes towards the cook. So nothing. Only just on the top.
Yeah. Sometimes we'll use the long ones to get that,
get that
changes
part,
in
yeah,
direction
okay.
of the smoke.
So you can use the long one so that you can also have the emissions from around the place,
Yes.
around the kitchen.
Okay.
Marcelo, pero no hay una regla de cuántos palos y cuántos agujeros.
There is a rule to the
Una
number
regla.
of points.
There is not a rule. We generally want to make sure you have good coverage of the plume, but there's not a rule about the number of holes.
Highest sample numbers you can, is that the rule?
Yeah, pretty much that's reasonable.
The highest number of sampling points you can. That's and getting a good sample of the whole plume.
Yes.
As you don't know this dilution, do you get relative values only or absolute values? You
Of
can calculate
dilution?
with the air. In the lamps, we know exactly.
Yeah. You don't know exactly how much dilution you have, but because the calculation is based on relative amounts on ratios, you don't. It doesn't affect the calculation, and it doesn't affect your results.
Yeah, if you add more dilution, each pollutant will dilute the same amount, and the ratio does not change. No matter what the dilution is, the ratio will always stay the same.
All right. I think we might want to go in and.
Yeah, you want to grab the filter?
Oh, yeah. That's the thing I forgot.
No, aquí tendrías que
All right. I think we can. Yeah.
Perhaps a stupid question. The
No.
difference between the uncontrolled cooking test and the kitchen performing test. You are doing this test just during one meal, and the controlled and the kitchen performing test is over a longer time. It's a principal difference.
I think the principal difference is that this is an emissions test.
Yeah.
And it's measuring you can measure events. Generally, we have been measuring event lengths, but the equipment is such that you could measure whole days, multiple days, depending on your research question.
Yeah.
What about the indoor air pollution meter now? The results from there and the one for the indoor air pollution. The indoor air pollution meter, IEP meter.
This,
What is the difference of this equipment to the indoor air?
That's a good question.
I think it's what you're sampling. You're measuring many of the same things, using many of the same sensors and methods. You're measuring particles and you're measuring CO in the same way that you do in indoor air quality. But the difference is where you place your probes. So for indoor air quality, you may place your sensors in a place where people, in a different place in the room that would represent how air is circulating in the room and the average concentrations.
My question is then which results do we use? You know, the result from the indoor air pollution meter and also this one, the one from here now. Which results should we use? You know, we can either use these props and the indoor air pollution meter. Yeah.
Yes, this is designed to measure the emissions of the stove, independent of what room the stove is. You can measure the emissions of the stove if it's inside or if it's outside. But the indoor air pollution meter is intended to measure the exposure. So it also includes the effect of ventilation.
And
I don't know if
in your
that
procedure,
makes sense.
you need to weigh the wood to take the moisture content of the wood, all this data, all this information, because
That's
you
useful
need-
and interesting data, but it's actually not necessary to process, to actually calculate the emission factors using this method. Again, because you're using ratios and you're using the amount of carbon to estimate the amount of fuel.
but you need the amount of fuel.
You do.
Of the
you,
test.
you need to, you estimate it based on the measurements.
Yeah, we're using the carbon balance method. So we're collecting the carbon and then we're calculating the concentration of carbon. And so that is independent of the actual weight of the fuel. That's a separate measurement, which we do, but it's not necessary to calculate the emission factors and the calculations that we do.
But maybe the number of wood that we fed, it also depends. Like if you fed a lot of wood, then certainly the emission will be high. Yeah, but I think we didn't talk about that. And if you fed 2, 3, or if you have enough secondary air, then more carbon will burn and there will be less emission.
Yeah.
Yeah, but some people they just fed, oh, I have to cook faster, so they fed more, and then in that case, so the emission will be too high.
Yes. But with this equipment, you can tell the amount of wood that they're feeding.
Might be we should have like a in the wood feeding hall. Yeah, hey, what percentage of should be the gap, so that the secondary air that passes in and have a better combustion. So I think we didn't talk about in that feed. So the amount of wood that fed and what percentage of the gap should be left for the secondary air.
We just saw the probe. I also have several questions. Perhaps you can show the whole
I think so.
methodology before we go into discussions.
Okay.
Because this is just the probe where the air intake
Yeah, I know.
and nothing else. And,
Okay.
if we go into
So
discussion,
we'll go inside and I'll show you the procedure to conduct the test. And then once we get the test going, then we can have more questions.
Okay.
Come on in.
Yeah.
Okay. So this is the equipment. We drilled a hole in the chimney to put the probe in. We're not using an isokinetic sample probe, but this is what I happen to have with us, so it'll work fine. Yeah. We know. So the first thing you do. So this is the equipment. The first thing you do is the day before, the night before, you make sure the desiccant is blue, you know that it's not expired. That dehydrates the air. And then we also charge the batteries, just regular maintenance stuff. And then, so before the test, we have to load a filter. We have to load the filters in. We run 2 filters, but today we're just going to use 1, just for simplicity.
Can you explain something? What this equipment is?
Yeah, so I mean the sample comes in here from the probe. It's drawn in from a pump underneath the panel, and it comes through the cyclone, which takes out the larger particles, and then it goes. A part of the sample goes through the microethylometer to measure the black carbon. The rest of the sample goes down underneath the panel where it's measured the optical particulate matter sensors. And then it comes up and goes through these filters. So we collect the smoke on the filters to weigh them. And then it goes through the gas sensors to measure the carbon monoxide and carbon dioxide concentration. And at the same time, we also, the smoke is too thick and the gases are too high in concentration for the sensors. Plus the smoke is hot. So we need to cool it down to ambient temperatures. So we add this dilution air. And it's also very moist. Like if you're measuring emissions right above a stove, there's a lot of water coming off. And so we add dry ambient air, we push it out into the sample and mix it to cool it down. And so we have a second stream of air coming in to dilute the sample.
Why do you need 2 sensors for CO2 and CO?
Well, so one's for the sample and one's for the background. You know, if we're putting in air from the room that has some carbon monoxide in it, we need to know that in order to correct our calculations.
So are you measuring the concentration or ratio in wet basis or dry basis?
The dry basis. It's all done
Dry
on dry
basis.
basis.
So dilution here is dry, but the stack emission that comes from the chimney. So what is the place that it dries or separates the stack emission moisture?
So it's not. We don't separate the moisture from the stack emissions. We just add a large amount of dry air.
Dry air.
And most of the flow is just dry air. And so that we have a relative humidity sensor, and you can see the relative humidity. As long as it stays below 50%, that's good enough for us, for our measurements. But yeah, that's the idea. Okay, so this is a quartz filter.
The filters are 47 millimeters.
Yeah. You can use it. Doesn't matter what size you use. That just happens to be the size of filter that fits in our scale. So usually we do this in a very clean environment where there's no dust. And
In the field.
well, yeah, we try to find a clean spot. It's not
He's
always easy.
got plastic suit he puts on it.
Yeah. And we clean, every test we clean the filter holders with acetone or some other solvent. And we always work in a sterile environment. But so we don't do this normally. But for the purpose of this demonstration, this is okay. So I put the filter in, then I have a data sheet here where I would like, I'll get out a data sheet.
Why you need to clean with acetone?
Because the organic vapors condense, build up onto the walls of the filter holder, and those we're measuring organic carbon on the filter, and so that will bias the next. If we don't clean it off every test, it'll bias the next test. You know, you'll be measuring the organic vapors from the previous test. That's the idea. So that's the data sheet.
And your work actually is to test the method or to develop and standardize the method, or you're just using these methods to...
Yeah, I mean the method is pretty developed, but I don't think it has been very documented and shared with everybody. So yeah, that's part of what we're doing is trying to, educate people on what we're doing and how you can do it. Together, people doing it too. But yeah, So the next step would be to turn on the equipment and set the flows. Oh yeah, no, before that, one thing we always do is we vacuum check the system. Like Jim had a really good presentation yesterday about a problem he had that could be solved by, that you would notice if he would have vacuum checked his sample lines. So I totally forgot to bring our vacuum checker, but it's this handheld device with a gauge on it, and you squeeze it a bunch of times and it pulls a vacuum. And so we can put that on our sample line and put the whole system under vacuum. And if it's holding a vacuum, then we know we don't have any leaks.
Check.
Yeah, a leak check. So that's something that I think everybody should be doing if they're measuring emissions. I wish I would have brought the thing to show you, but you should definitely get one, even if you have like a LEMS or whatever you're using.
What do you call this?
The first person that made this called it the Arachne.
Arachne.
Yeah, so that's what it's called. Ambulatory Real-Time Analyzer of Climate and Health-Related Noxious Emissions. That's what it's called.
So was it designed for stoves or?
Yes.
Okay.
Yeah, and it's also used for kilns and others. It's been used for other things too, but mostly stoves.
And have you deployed it in any of the fields yet?
There's about 8 different countries we've used it in. We have hundreds of cooking tests, like several hundred cooking tests in about 8 different countries.
Honduras is actually the first country that's ever used it. I think
Yeah.
Tim's first
Yeah,
trip
you're
was to
right.
Honduras.
No, this
Yeah.
makes sense because
So I'll turn it on and set the flows now. So we use the bubble meter to set the flows. Oops.
We would see the video this afternoon. I was gonna say, go ahead and step in now, because I got a quick shot. You guys. Yeah, it's difficult.
How many different places do you have to check the flow?
Like 4. We check the flow through the aethalometer. We check the flow through each filter, and then the bypass flow for using that, and then they do a double check and check the flow in the inlet to make sure it adds up to all the other flows that we just checked. And if it doesn't, then we know there's a problem. I'm going to start logging the data.
Just made the homework super closer. Where it was perfect actually. All right. Or you know what? It's your turn. Maybe I'll do this quickly. I'm just gonna reach over and just check this in your
Nice.
Okay. Cool.
Yeah, that's great. Okay, so now we're logging data. I'm going to set the flows. Just real quick. So we put the quartz filter in, so I'll put the flow on the quartz filter. Close off the bypass. Who's used a bubble meter before? Who's seen one? Just half the people. So I'm going to set it to 1500.
You have the right amount of soap in there already?
Yeah. We don't change the soap very often.
what's the logic behind 1500?
What?
1500, why 1500?
Because this cyclone requires a flow of 1500 in order to separate out, in order to give a PM 2.5 cut.
Oh.
You're regulating the airflow?
Yeah, that's a needle valve.
How much do you need?
1500. So there, it's about right. So that's good enough for now. 1490.
So you were calibrating this rotavator for rear, right?
What?
You were calibrating this rotavator for airflow.
Yeah. Well, no, I'm not calibrating it. I'm setting the flows. We have a digital flow meters that are also logging the data and showing the flow here. But they're hard to keep calibrated because when we do sampling, we're always changing elevation. And every time you change the elevation, it changes the pressure and it changes the volumetric flow rate. So we usually just use those to watch the flow to make sure it's stable, and then we set the flow with this. That's kind of the procedure we've been using, and it seems to work pretty good. Yeah. Okay, so now we're ready to go. So the next step, I think, let me just check my list. We take a background period. So we need to measure, just get a measurement of the clean air in the room. Right now, it's probably going to be pretty high CO2 because everybody's breathing. And so usually that takes at least 10 minutes. How's it going, Rainey? So, usually we wait about 10 minutes, but since we don't really have that time, could you guys just move your clocks forward 10 minutes? Okay. So now we're going to start the test. So I just stick the probe in. Usually it doesn't look like that, but that's how it's going to look today. And we can
usually we fix it like make it seal it.
Yeah.
Okay.
Yeah, it doesn't need to be too sealed, but it's better than that.
And in case there's no chimney, then we'll use the probe that.
Exactly. Yeah.
And you can also sample from the roof.
Why I can use more or less the same probe with IRP. The holes are probably too small. The IRP meter has an air intake. Just connect it also with a sampler.
Yeah, I guess this is, I don't know why you do the probe.
It's the fire starter. I forget. You have to ask one of the people, the Hondurans, what they call it. But it works really good.
Yeah. Some parts like the northern parts of India, they have it. I guess in Nepal also. Yeah, in Nepal also we use pine. But the other parts of India, they generally use either pancakes or kerosene.
Yeah.
The cooling.
Thank you. Oops.
Did they mention that they have a problem with cooling at the?
Well, they use dilutionary.
Oh, I know. I was thinking more actually cooling and condensing, just the fact it's all that metal.
Yeah, I don't know. Yeah, about condensing.
Okay, that's good.
Is there not a problem with cooling and condensing in the probe itself, right?
Yeah, usually we bring the dilution in as soon as possible, like really close to it.
I was thinking with the Iraqi with a bigger probe. Is that not a problem?
Is
It's-
this air intake?
Yeah, for the dilution, yeah.
Yeah, but it's directly
Oh, that's okay. Okay, it's fine.
So the dilutionary is
runs faster.
on that.
Yeah.
Oh, okay.
I mean, right now, the way I have it set, there's 1,500 cc coming in here and 1,400 dilution. So there's only 100 coming from the stove even. So yeah, in this case, I mean, it's definitely, condensation is going to be a problem. That's part of the protocol, is to every day to clean out the probes. They don't really get that dirty as you would expect, but yeah, condensation is a problem. It's kind of unavoidable in that sense. So that's the idea. I don't see, let's get this fire raging, get some emissions going. So yeah, PM.
Which one are you looking at?
Oh, so that's CO2.
What was the baseline in here?
500.
Yeah.
Is that pretty nice?
I'm gonna turn it.
is een neffelometer.
Need some more firewood?
No, this is plenty. Oh, I see the problem. I didn't connect this. Sorry. I was talking while I was setting it up. Now it should go really high.
Every second you send the data here.
Yeah, once every 2
1
seconds.
second?
Once every 2 seconds.
Mhm.
Yeah, if you want to see the data logging, that's all the sensors.
Yeah.
There's like, the gas sensors, and then there's a bunch of temperature and humidity sensors and flow sensors throughout the system. Yeah.
10 more minutes till rotation.
Okay, so
For those of you who are interested, there's another black carbon measurement being presented in this room over here.
So yeah, this is gonna run. We should go. You guys should go into the other room now.
Yeah.
And then you can come back here and look at it at the end if you want. What?
Okay.
What's the other room?
Oh, there's a PowerPoint presentation.
What's happening here? Or different?
Yeah, he's gonna show his field equipment, and then Cheryl was gonna show some. She was gonna show some things on her computer, but I don't think there's time.
So it means PM red and PM
Infrared. This one is a 635 nanometers laser, and that one's at 880, because this machine is 880 nanometers, and so I needed.
This is for black cover.
Yeah, so I wanted to measure scattering and absorption, so I can calculate the single scattering albedo at the same wavelength. So I added that other infrared sensor.
So the wide scattering sensors are underneath the panel?
Yeah.
Okay.
Yeah.
Once the filter is exposed, what we do is we put the filter on a reference card. And this reference card has gray calibrations that have already been determined in the laboratory with equipment like they're using for a certain region. You put the filter on the card, and then you just take a picture of it. We are using in the field just a regular cell phone. Take a picture, and then you send it to an email address. And the email address is connected to our server that will then process the information on the reference card and analyze the color of the filter and give you an estimate of the black carbon for almost no cost. The cost is really just for the pump. And then this is really just the cost of sending an email. Very inexpensive. It's about...
You have to pay per analysis?
No, so calibration is interesting. So if you have some very different kind of particles you want to be measuring, if you pay for 20 or 30 analyses by thermal optical analysis, we can take those data and create a reference card specifically tailored for your application. So we've done this for a couple of different places so this was our first calibration with Indian and California data, but we've been working with some other people, even using different instrumentation. I can't see, but this is a PASS unit, which is an instantaneous optical system.
Sending the photo is only necessary to calibrate.
No, so we've already got a calibration file in our server, in our computer, and then you send the photo to analyze the filter. So now you can analyze many, many filters without any additional cost. Make sense? So we have already established a calibration with your exposed filters and put that in the computer. And then when you send the email with the exposed filter, the computer will take a look at it, analyze it, and then give you a result. And I have a photo.
I understand this perfectly, but I have 100 probes.
Yes.
So I take 100 photos and send 100 emails?
Yes. Yeah. It's a little...
And this is for free?
This is for free. This
Why?
is for free.
It's necessary for
We don't believe it.
with the use of it's necessary to send all this photo for calibration.
First we get some calibration, and then the photos you just get the analysis.
So for cook stores, like measuring black carbon for cook stores, the calibration is already done, so it's free. If you want to do it with something else, as Eric is saying, you'll have to go for the calibration, and maybe if you get funding for that, it can also be free in the long run.
That's true. But we have some calibrations for stoves like this, but with a forced draft
For
stove.
any stove we have the calibration, right? It's basically black carbon coming out of stoves. So any smoke coming out of stoves can use this kind of a method.
And an interesting part of that, though, is sometimes the smoke it has some organics as well. And so we've been playing around with the color. So this is mostly grayscale. This is like a lightness darkness scale. We've been analyzing now color because you're taking a color photograph. We can look at some color signatures, and what we've been playing with is trying to get an idea of the organic carbon content also. Just a general idea, maybe where it's coming from. So that graph there on the left-hand side, we've got some data from India that is falling in this color region over here. We've got some other data from Baghdad that's falling over here. So we've got different carbon sources that have slightly different colorations.
Those yellow color when people burn dung cakes.
Yeah. So that's some organics and other compounds.
So dung cakes is the source of that yellow color in the filter.
We're looking at trying to characterize some of those organics and seeing if we can at least tell maybe a source of the organics or not.
Okay, I understand the methodology, but I live in Africa. And you say just get a pump, get a filter holder and such a box, and it's ready. It's a little bit difficult to get this in Africa. So my question is if there is somebody who can provide this completely ready.
This specific box, not anymore.
But a similar one with the same function.
I have built my own. You can purchase this filter holder.
Yeah, but I can't purchase in Dakar.
Okay.
Unfortunately,
I don't
the world is bigger than the US.
You have bigger problems than I can solve. I don't know.
No, but the problem
hire
is
somebody. I mean, our technician Carl, you can hire him.
But this is what I'm aiming to. That perhaps you offer from here the package.
Sure. I mean, we'll put on the list.
Yeah.
So somebody can just courier, because these guys courier to us in UP, in Uttar Pradesh, in India. Like we get it in our village through a courier. So you just take it out, connect it, and start using it.
There must be a plug-in,
But this is my question.
Who can provide these?
So I don't know where you can buy them off the shelf. If I wanted to make one, I would hire one of our engineers to build it for me.
With a local source, maybe, yeah.
But there probably are much cheaper versions out there somewhere.
In the market, there is some personal exposure system like this, but it's not like this, but it's the same
that you can
cycle,
wear.
maybe the same system. It's possible to use that.
Yes, any kind of sampler.
The same, but with another kind of pump and other way, but the same
as long as
system.
you expose a filter, no problem. One issue is the filter. This method does saturate, so the maximum amount of black carbon you can measure on the filter is approximately 20 micrograms per square centimeter. But that's pretty dark, and it's also a lower limit because it is a cheap cell phone, and so there are limits to the photography.
You can calculate how much black carbon is on this filter.
Plus or minus about 20%.
But then I have to know how much air went through to get this concentration, this amount of black carbon.
Yeah, you have to still do some calculations.
Yeah.
You know the flow rate for the pump.
If I have a pump.
You have to have a pump.
You need some kind of resolution of the picture.
No, in fact, actually, lower resolution starts to integrate the filter colors, and so there's actually high resolution is worse than low resolution. Not too bad, yeah. And we can invite you guys to try. I'm the only Eric, right? So you can email me and get all the information you need.
You're from Next Leaf?
I'm from Next Leaf.
So use the pump?
The pump is the only. This is the only pump we had. It was made by UC San Diego, and so they don't make those anymore. Unfortunately, I wish that we're buying some personal pumps from personal exposure pump. But they're like $800 each or something expensive.
Yeah.
The pumps are not cheap.
With the pressure drop, you'll start getting changes in the flow rates.
Oh yeah, it's a crude method, but it's really inexpensive, and that's the nice thing about it. So maybe if you have 100 places you want to measure and you don't have the resources to send each filter to get thermo-optically analyzed, or you can't buy a PAMS, then this is maybe some sort of a method to get some data out of these systems. I have one more thing I would like to talk about. Actually, is this. So this is my representative gasifier stove, right? Right. This is your an I button for measuring temperature, a stove usage monitor, sums that will just keep the temperature log. We built one ourselves also that has this connected to a mobile phone, and it will upload the data as well if you want to do that. This is what we're doing in India, is transmitting the data to the server. But it doesn't really matter what you're using in terms of measuring temperature. We are investigating, it's pretty easy to measure cooking time with the temperature, right? The temperature rises, the temperature falls. You can calculate in various ways the cooking time. What we've been playing with is trying to estimate how much fuel you're using also in the same stove. And let's see, I want to show, oops, no, I'm sorry. Well, let's see, this graph. We have a single stove in our laboratory, and we've been doing various cooking trials with wood, various different kinds of wood at different intensities and different lengths of time. And we've been measuring the energy balance of the bar. So basically, how hot it gets, what is the ambient temperature, and so how much it is radiating heat, how much is losing by conduction and convection, and just doing a relatively simple energy balance based on the temperature signature of this. And with an energy balance, calculating what is the percentage of the fuel that is used to heat the stove or heat this bar. And if that is constant, we may be able to actually predict fuel usage by just using a stove usage monitor. What we've only been doing is these little stoves, and I would love to be able to get some data from something like a plancha stove. I don't have any access to these. But if anyone is using...
This is for one pot stove, this system.
This is for this type of stove, and this is like a portable, just something you can put in here, and it's out of the way so it does not interfere with cooking. This would be, I don't know, where do you put the sums on these kinds of stoves? You put it like on the chimney or something?
It
Should not be. Where it's warm.
It should not be.
There's temperature, yeah. If it gets hot,
Up to 110.
yeah, so it depends where. Every stove is different for how insulated it is and blah blah blah.
So ideally we can actually do some sort of rough calculation as well. You don't think. I know you're a disbeliever, but I'm convinced actually that this is going to work because.
Oh, I'm not disbelieving. I'm saying that every time I use any device, it's always more complicated to use than I think it's going to be when I first start. So he was asking me because he's maybe even talking about trying to get us to work with him on this, and I'm saying, well, just assume that there may be challenges, engineering challenges in any device.
Always challenges, and so every stove would have to be calibrated, but our stove is repeatedly just, no matter how much we cook with different fuels, it's actually lying on a really nice calibration scale for estimating fuel use.
It's possible to calibrate this system for any stoves and any firewood.
I think so. We did two fuels. We did wood, which is a nice straight line, and charcoal, which also fit a very nice line.
Maybe for a cook stove like this, you need more sensors, maybe?
Possible, yeah. I have no experience with these, so maybe a sensor
the
here,
head
sensor here.
It's not the same in all the bodies.
Varies very much, yeah.
Very much, but as long as you get the same response.
Are you calibrating at different fire counters?
Yes. So some of these cooking events were very short and intense, and then some of them were long and low power, and it seems to be pretty consistent. It's kind of maybe not surprising because it's just a physics problem, right?
Hate to be the bad guy.
Mm-hmm.
Rotate.
All right.
Rotate. So you guys group number 1. Yes, station number 2.
So please.
This method is perfect for us.
Because it's cheap, yes? Okay.
It's not cheap because we have to get a pump. And even a pump for $10 might be very expensive for us.
Oh my.
That's always the same discussion. People come with a stove, they say, oh, I have a marvelous stove, but it's not accessible for people. And therefore I'm insisting
Good.
to provide something, the complete system.
Mm-hmm. And
perhaps with somebody who could build this and...
I agree. We tried the people in San Diego. We were very excited because they were building these pumps, and then they stopped. It became not important to them, and so we were very disappointed. We were looking for a way to get an end-to-end system that is inexpensive.
Which part of Africa you are in? Which part?
Senegal.
In Senegal. Okay.